Algorithms on graphs, minimum cost spanning trees revisited. We saw an algorithm on graphs in Chapter 10. That algorithm, called the Kruskal's algorithm, took a connected simple graph whose edges were assigned a cost or weight as the input and returned a minimal cost spanning tree of G as an output. In Chapter 10, we were concerned about the greedy property of the algorithm. That is, the fact that in each step, the algorithm took the edge that increased the short-term cost the least. That is, in each step, the algorithm chose an edge that did not create a cycle and had the minimal cost of all edges with that property. Now we will consider that algorithm from a different aspect. Our goal is to decide how many steps the algorithm takes. Foretelling the need for a unified approach that we will introduce in the next section, we point out that what a step is needs a little bit of explanation. In the sorting algorithms of the previous section, we simply counted the comparisons. In Kruskal's algorithm, however, it is not so clear that we should count. Indeed, choosing an edge from a graph is easy, but choosing an edge that does not create a cycle is more difficult. In a very large graph, because we need to make sure that indeed no cycle is created and that in itself can take a long time if we do not have an efficient method to do it. Let us discuss an efficient way of running the Kruskal algorithm. As we said, each round of the algorithm will look for the lowest cost edge that can be added to the set S of edges already selected without creating a cycle. This means that if there are several edges that can be added without creating a cycle, then we have to look for the one with the minimum cost, finding a minimum cost edge in each round and then forgetting the results of all comparisons made in the process seems wasteful. It is therefore sensible to sort all edges of G at the beginning of the algorithm. As we have seen in the previous section, this can be done in big O of E times log base 2 of E steps, where E is the number of edges of G. Let edges be the set of collections of E1, E2, E3 until EE, where the last EE is with index capital E, be the obtained list of all edges of G in non-decreasing order of their costs. Now, in the first round of Kruskal's algorithm, we choose the edge E1, and in the second round, we choose E2. As G is simple, E1 and E2 never form a cycle. The third round is more complicated as E1, E2, and E3 could form a cycle. If that happens, E3 is rejected and E4 is selected. However, as we proceed further, we need an efficient approach to decide whether the next edge of edges is eligible to be chosen or not, that is, whether its addition would create a cycle or not. It would take very long to consider every possible subset of edges containing the newly chosen edge and verify that they do not contain a cycle. Instead, we propose the following. From the beginning of the algorithm, let us keep track of the connected components of the graph T of selected edges. That is, when we choose E1, let us put the two endpoints of E1 into a new set C1, indicating that they are in the same component of T. After selecting E2, put its endpoints in C1. If a 2H graph with edges E1 and E2 is connected, and put them into a new set C2 if that graph is not connected. Continue this way, that is, in round I, scan the still unused edges of edges until you find the first edge whose endpoints are not in the same component Ci. It could be that they are in different components, or it could be that one or both of them are not in any components yet. Add that HEH to T, discard the edges preceding EH from edges. If they could not be added to T before without forming a cycle, they cannot be added to T now without forming a cycle. Then update the list of components, that is, if neither endpoint of EH was included in any CI before, create a new component with the endpoints of EI. If one of them was in Cj and the other one was in no component, add that other one to Cj. Finally, if one endpoint of EH was in Ci and the other one in Cj, then unite Ci and Cj and add both EI and EJ to the obtained component. Rename that component so that it inherits the label of the larger of its predecessors, that is, the component which had more vertices in it. This assures that the graph T remains cycle-free, since we never joined two of its vertices in the same component by an edge. Before counting the steps in this second part of the procedure, let us consider an example. Example 17.14. The above implementation of Kraskow's algorithm applied to the graph of figure 17.1 runs as follows. 1. Start with the graph shown in figure 17.1 with the costs assigned to the edges, but not yet the labels EI. 2. Sort the edges according to their cost. Obtain the list edges equals to E1, E2, E3, and so on until E11. 3. Select E1. Create the component C1 equals to A and B. 4. Select E2. Create the component C2 equals to G and H. 5. Select E3. Add E to C1 to get C1 equals to A, B, and E. 6. Select E4. Unite C1 and C2 to get C1 equals to A, B, E, G, and H. Then we have to skip E5 because they might create a cycle. 7. Select E6. Note that E5 is ineligible since its endpoint both belong to C1. Add F to C1 to get C1 equals to A, B, E, F, and G, H. 8. Select E8. Note that E7 is ineligible since its endpoint both belong to C1. Add D to C1 to get C1 equals to A, B, D, E, F, G, and H. Select E12. Note that E9, E10, and E11 are ineligible since their endpoints both belong to C1. 9. End with the tree whose edges are E1, E2, E3, E4, E6, E8, and E12. Returning to the question of how many steps the Kraskow algorithm takes, let us say that for this algorithm, a step is whenever we do something, that is, put a vertex in a component, unite two components, or check whether two vertices are in the same component. Note that in each round, we have to scan at most EHs before finding the minimal cost H that is eligible. After finding this HE, there are two possibilities. If E will not unite two existing components, but create a new component of two vertices or add one vertex to an existing component, then we can record that in a constant number of steps. Indeed, we spend at most 2 steps adding a vertex to one or two components. If E unites two components, say Ci and Cj, then we change the label of the vertices in the smaller component to the label of the other component. This may take as many as n over 2 steps. However, if X is a vertex whose label changed this way, then the component containing X at least doubled in size. This cannot happen more than log base 2 of n times for any X. So each X will change labels no more than log base 2 of n times. Therefore, the number of all changes of labels is not more than n times log base 2 of n. To summarize, it takes big O of E times log base 2 of E steps to sort the addresses according to their costs. Then it takes big O of E plus n times log base 2 of n steps to find the minimal cost tree. Therefore, the total number of steps needed is big O of E times log base 2 of E, since our graph is connected, so E which is greater than or equals to n minus 1.